This is the third and final lecture in our mini-lecture series on descriptive statistics. In the first two lectures of the series, we discussed measures of central tendency and measures of variability. In this lecture, we will focus on what it means for a data set to be normally distributed, how to determine if a data set is normally distributed, and how to compare your sample results to the population with different levels of confidence. By the end of this lecture, students should be able to describe what it means for a data set to be normally distributed, explain the meanings of the terms skewness and kurtosis, and describe the use and purpose of confidence intervals. Measures of central tendency and measures of variability are both considered point estimates. Both measures of central tendency and measures of variability produce single numbers. Measures of central tendency allowed us to better understand the center of the data, and measures of variability provided insight into the spread of the individual values within the data set. The data used to compute measures of central tendency and measures of variability come from our data set, which is composed of a sample of the population. Even when we are very conscientious about our sampling methods, we can never ensure that our sample will accurately reflect values in the population as a whole. Therefore, we need to address this limitation. There are two ways for us to address the limitation. First, we must assess our data set to see if our data is normally distributed. Second, we can create confidence intervals or boundaries that we think the population mean will fall between. We will look at both of these procedures and their associated concepts in detail in the upcoming slides. As we have done thus far in this three-part discussion, we will continue to use our course data set to help you better understand concepts related to normal distribution, standard normal distribution, and confidence intervals. Once again, I have provided a copy of the data set here for your convenience, and in this lecture, we will be focusing exclusively on the column related to years of nursing experience. One of the functions of descriptive statistics is to help us understand whether the distribution of a continuously measured variable is normal. We care about normal distribution because many human characteristics follow a normal distribution. The normal distribution is just one of many marks of a divine creator shown throughout the discipline of mathematics. Furthermore, we care about normal distributions because most statistical analysis is going to be based on an assumption of a normally distributed sample. So, what does it mean for a sample to be normally distributed? When a distribution or the numbers within the sample data set are normal, the distribution is symmetrical, meaning the area on both sides of the mean is equal. In other words, just like in the picture on this slide, the mean is the highest peak in the distribution, and 50% of the individual data values will fall above the mean, and 50% will fall below the mean. The spread of the distribution is presented in terms of the standard deviation. And if you recall from our discussion of the empirical rule in our lecture on variance, any normal distribution, 68.3% of the values will fall within one standard deviation of the mean, 95.5% will fall within two standard deviations of the mean, and 99.7% will fall within three standard deviations of the mean. And just to better help you understand this graph that you are looking at, mu, the symbol that looks like a backwards U, is the mean, and theta, the symbol that looks kind of like an O with a hat, is the symbol for standard deviation. It is very important to understand that no data set is ever going to be exactly and perfectly normally distributed in reality. However, we can assess our data set to determine if the distribution is centered well enough around the mean to be considered normally distributed. The first step in assessing for normal distribution is similar to the first step of patient assessment. Just like you want to look at your patient, you want to look at your data. And the easiest way to look at our data is to make a histogram to see if the data set appears to be normally distributed. For some data sets, a histogram will quickly bring to light that the data is not normally distributed. Some data sets you will easily be able to see that the peak and the mean is not in the middle, but rather it is shifted or skewed to one side or the other. For other data sets, it may not be that easy to tell just from the visual representation alone if our data is normally distributed. The data may look normally distributed, but we will need to do further calculations to confirm this. Along with visually looking at a histogram, you should also perform statistical measures of skewness and kurtosis. Skewness is a measure of whether the data set is symmetrical or off-center. In other words, is the mean in the center of the data set, or is the mean skewed towards one side or the other? And when we discuss skew, we are looking at what side the long tail is on. So in the picture on this slide, we have the blue normal distribution, and we can tell that our mean is in the middle. We have the red left skewed distribution because we have a long tail going off to the left. Our data mean is pulled to the left. On a right skewed data distribution, our mean is pulled off to the right. We have a long scale to the right. The other thing we want to look at is kurtosis. Kurtosis is a measure of how peaked the distribution is. A normal distribution is said to be mesokurtic. A distribution that is very peaked is said to be leptokurtic, and a distribution that is very flat is said to be platykurtic. So, what are we looking for? You are not going to be expected to calculate measures of skewness and kurtosis. You will use statistical technology such as Microsoft Excel or IBM SPSS. In general, a distribution is normally distributed if the skewness is between -1 and 1, and the kurtosis is centered around 3. So let's take a minute to look at our distribution for years of nursing experience. As we calculated in our lecture on variance, our mean is 12.36 years with a standard deviation of 12.40 years. When we look at our histogram, we can instantly visualize that this is not normally distributed data set. We can instantly recognize that our data set is skewed to the right. Notice that long tail that we have going off to the right with our data set. Our skewness is 1.27, which is greater than 1, which means that our data set is definitely skewed to the right. Our kurtosis, when we're looking at our data set, it does in general look pretty flat, except for that peak in the range from 1 to 5.3 years. Our kurtosis is 0.07, which is much less than 3, meaning that our data set is platykurtic. So we would say that we have a non-normal distribution that is skewed to the right and platykurtic. So how does our sample compare to the population of years of nursing experience? As I have alluded to a few times already, your sample mean and the population mean likely will not be the same. If you were to take multiple samples, your mean for each sample is probably going to be slightly different. If we looked at the average years of nursing experience of nurses on different units across the United States, we're likely going to come up with different averages for each sample. So we need a method to compare the samples to each other and to compare an individual to the sample as a whole. But this is really challenging because our samples probably aren't all going to be the same size, and we already know our samples aren't going to have the same mean and standard deviations. So we're left with comparing apples to oranges. But we're not. There is a term called the standard normal distribution, and the standard normal distribution addresses this issue and allows us to compare samples of different sizes with different means and different standard deviations. The standard normal distribution provides a way to place all of the values or the scores or the data pieces on a standardized normal scale. In a standard normal distribution, we have assumed that the mean is 0 and the standard deviation is 1. We can then compute a standardized score called a z-score that allows us to translate any given score from a normally distributed sample of any size and a standard deviation to a score on the standardized normal distribution. Thus, a z-score tells us how many standard deviations an individual score is above or below the mean. Once a z-score is known, a z-table can be used to translate a z-score into a percentile rank. Do not worry, you will not be computing z-scores on your own, and you will not be needing to use a z-table. However, I did provide you with the formula for the z-score. The z-score formula is calculated by taking x, which x is the number you want to learn about, whether x is the individual score or whether x is your sample's mean minus mu, the population mean, divided by theta, the population standard deviation. Again, most people will rely on technology to provide you with both the z-score and the percentile rank from the z-table. So let's connect this back to the empirical rule and what we already know about a normal distribution. We've already discussed that 68.3% of values will fall within one standard deviation of the mean, 95.5% will fall within 2 standard deviations of the mean, and 99.7% will fall within 3 standard deviations of the mean. Therefore, when we are calculating a z-score, 68.3% of z-scores are going to fall between plus and minus 1 because remember, the z-score is the number of standard deviations from the mean. So then 99.5% of your z-scores will be between plus and minus 2, and 99.7 will be within plus and minus 3, which explains why most of your z-tables have a range between negative 3.5 and positive 3.5. It is very unlikely that you are going to get a z-score smaller than negative 3 or larger than positive 3. If you get a z-score that falls out of the range of plus minus 3, you know that this is an extreme outlier. As I mentioned, you are not going to be expected to calculate a z-score. What you need to understand about z-scores is that positive z-scores indicate how many standard deviations the value is above the mean, and negative z-scores indicate how many standard deviations the value is below the mean. The smaller the absolute value of the z-score, the closer it is to the mean. The larger the absolute value of the z-score, the farther it is from the mean. So some of you may feel like I am talking a foreign language right now. So let's take this back to our sample of average years of nursing experience. I know we discussed that our sample was not normally distributed. However, for the sake of being consistent with the data set we are using, we're going to assume our sample was normally distributed. And we want to look at how did our sample mean compared to the population mean. I looked up some information and I was able to gather that the population mean for average years of nursing experience in the United States is 14.66 years with a standard deviation of 12.35 years. I have that in a table compared to our sample. And it appears that our sample is pretty close to the average. But how close is our sample? Well, I can guarantee you there were more nurses in the population than our sample of 25 nurses, so we need to compute a z-score. So for our z-score, we are going to take our sample mean minus the population mean divided by the population standard deviation. This gives us a z-score of negative 0.19. What does this mean? Well, the negative means that our mean is less than the population mean, which we could tell just by looking at our mean and the population mean. But how much less? It is 0.19 standard deviations below the population mean. Well, that's pretty close to the population mean. But how close is it? So if we look at a z-table, and I have an excerpt from a z-table here, our z-score is negative 0.19. So if we go across the row for negative 0.1 and down the column for 9, our spot for negative 0.19, which I have circled, is 0.4247. What does that mean? That means our average is in the 42nd percentile. So our average is about 8% lower than the population. So our sample is fairly representative of the population. On the previous slide, we used the population parameter, which remember is the average for the population, and the population standard deviation to compare our data set to the population. However, I've been stressing throughout this lecture series that the population parameter is often unknown. Yet, one of the most important questions that descriptive statistics is used to answer is how well our sample represents a population. This begs the question of how do we know how well a sample represents a population if we don't have information about the population parameters? To address this, statisticians create boundaries or a range of estimates that they think the population parameter will fall between. These boundaries are created based on how certain the researchers want to be that the population parameter is located within the boundaries. Researchers can choose if they want to be 90% certain, 95% certain, or 99% certain. The term for this level of certainty is called confidence levels. For most research, the confidence level will be set at 95%. So most researchers want to create a range of estimates that they are 95% certain that the population parameter will fall between. This range or bounds is computed using a complex statistical formula that I have listed on the page. The formula takes into consideration the sample mean, the confidence level desired, which I have abbreviated as CL, the standard deviation for the sample, and the sample size. Explaining the proof behind how and why this formula works would be far beyond the scope of this course. What I want you to understand for this course is the relationship between the confidence level that is chosen and the confidence interval, or the range of data values. Most of the time, as I discussed, a 95% confidence level is going to be chosen, and a 95% confidence level for most research is considered acceptable. The more confident we want to be in our results, the wider our confidence interval is going to be. If you think about that, think about it as if you want to catch the most number of fish. So the amount of fish you want to catch is your confidence level. The bigger the net, the bigger the confidence level you want to catch more fish, the more fish you can catch. So the wider we make our net, the wider we make our confidence level, the wider our interval is going to be. Because a wider confidence interval increases the likelihood that the population parameter is going to be captured. And we're going to look at this on the next slide in a different way. I wanted to include this visual representation for you just in case what I was saying on the previous slide was not making sense. So on the far left hand, we have our population, and you can see there's a line for the population mean. Moving towards the right, we have our sample, and you can see that our sample mean is less than our population mean. And we want to determine with confidence that we are going to capture the population mean within our sample. And you can see in the gray that we have a 90% confidence interval, and that just barely captures the population mean within it. It definitely captures our sample mean, but it barely captures the population mean. When we move out further to the right and we look at the maroon, we have our 99% confidence interval. Notice that the 99% confidence interval captures our sample mean, everything within the 90% confidence interval, including that population mean, and it captures even more of the data beyond what the 90% captured. Notice also that the 90% and the 99% confidence interval leave out some of the population and leave out some of our sample. This is because we are leaving out those outliers. But the bigger our confidence interval, the more of the values of the population we are capturing. So, in case you're still struggling a little bit with confidence intervals and confidence levels, let's bring this back to our data set. Again, I do not expect you to do this calculation by hand. I have computed the calculations for you. And just for reference, I have included our table with our sample and the population. Again, we don't know the population mean or standard deviation when calculating confidence intervals. And I also provided you with the part of the formula that has to do with the z-score for the confidence level. This is standardized. For a 90% confidence level, that data piece will be 1.645, for a 95%, 1.96, and for a 99%, 2.58. If you were a statistician, you would have these things memorized. Again, for your work, a computer technology will help calculate this. However, we say we want a 95% confidence level. We want to be 95% certain that the average years of nursing experience that we are going to capture that. So we can be 95% certain that the population mean for years of nursing experience is going to fall between 7.5 years and 17.22 years. And just to show that this does work, if we look back at our population, 14.66 years, hey, it does fall within that 95% confidence level that we wanted. So our 95% confidence level gives us a confidence interval of 7.5 to 17.22 years experience. In summary, descriptive statistics are crucial for both summarizing and understanding a data set. Descriptive statistics provide us with a concise overview of the main characteristics of a data set, and they allow researchers to identify patterns, trends, and potential errors or outliers in their data set before moving on to a more complex statistical analysis. If we did not have and use descriptive statistics, large data sets would be difficult to interpret and important insights could be missed. As a reader and reviewer of literature, descriptive statistics also lets you understand how well the sample for the study relates to the population where you work. So, measures of central tendency, our topic from part 1. These are things like the mode, the median, and the mean. They indicate the typical value, the center value in a data set. The measures of variability, the range, the interquartile range, the variance, and the standard deviation tell us how spread out the data is, and the degrees of freedom talk to us about the variability within the data. Together, measures of central tendency and measures of variability help us to understand the overall distribution and characteristics of our data. Moving forward from that, we want to be able to describe if our data set is normally distributed. A normally distributed data set follows a bell curve where half the values are below the mean, half the values are above the mean. This is important because most statistical analysis relies on a data set that is normally distributed. And therefore, when your data set is normally distributed, the empirical rule, the rule that 68.3% of values fall within one standard deviation, 95.5% fall in two standard deviations, and 99.7% fall in three standard deviations can be applied. When we are looking at a normal distribution, we begin with a histogram, and then we assess for skewness and kurtosis. Because every sample is going to have different means and standard deviations and sizes, even when they are normally distributed, we need to be able to compare individual values to a sample, and we need to be able to compare samples to each other, which is why we use the standard normal distribution, and we can use a z-score to compute how for an individual data value where it falls in comparison to the estimated population mean. Similarly, we use confidence intervals to see how representative our sample is of the population. And we are able to choose a 90, 95, or 99% confidence level of how certain we want to be that the values in our sample are representative of the values in the population. And I hope you found this series to be helpful and beneficial. This is the foundational information upon which we will build inferential statistics in our upcoming modules, and I will see you then.